Before we start, we want to big up New Scientist Live, our award-winning festival of ideas and discovery.
The ultimate place to expand your mind and feed your curiosity is returning to XL London on Saturday the 12th and Sunday the 13th of October. Over 80 exhibits, over 70 incredible speakers across 5 stages. It's everything you love about science, technology, and the world around you.
And if you can't make it to London, we'll be live streaming the talks so you can join us from the comfort of your own home. Hear some of the world's most interesting people as they discuss everything from the Big Bang to mental health, the magic of mycology, and the world's biggest flowers. If you're curious about life, the universe, and our place in it, there is a talk for you at New Scientist Live.
For more information, visit newscientist.com/NSLivePod.
Hello and welcome to your weekly dose of essential science news from New Scientist. I'm Rowan Hooper, and with me in the studio this week is our US editor, Chelsea White. Hello,
Hi.
Chelsea.
Hello,
How
good to
you doing?
be here.
Jet lag?
Yeah, I'm very well. I'm very underrested.
Well, stay with it.
Yeah, this will wake me up. On the show this week, we're discussing the impact of Hurricane Milton on Florida, and we're hearing how the increase in life expectancy that we've been enjoying is slowing down. And we're going to learn about 2 billionyearold microbes living in rock.
We're going to start, though, with a massive story this week. And it's a paper published in Nature that it basically undermines a key part of the way that we're planning to tackle climate change. That idea is that we'll exceed the target of 1.5 degrees of warming, we'll overshoot it, but then we'll be able to get back down to 1.5 by removing carbon dioxide from the atmosphere. Michael LePage is here. Michael, you've reported this for us. The work this week, basically, it shows that there's no guarantee that we'll be able to come back after overshoot. And even if we can, then some changes can't be reversed, right?
Yes, I think for me there are 4 big points in this paper. So the first is there's no guarantee that warming will stop even if we stop adding CO2 to the atmosphere. So the danger there is that we trigger these positive feedback effects, such as the melting of permafrost. That means warming continues even after we stop adding CO2. Now, the second big point in this paper is that even if we can stop warming, if we want to cool the planet down as well, we've got to remove these huge quantities of CO2 from the atmosphere. And to give you some numbers, so at the moment, all the global emissions are currently around 40 gigatons of CO2 a year. That's 40 billion tons. That's from all the cars and industry and planes around the world. Now, if we overshoot 1.5 by just 0.1 degrees, we'll need to remove more than 220 gigatons of CO2 to cool the world back down. So that's 5 years' worth of current emissions. So that's a huge amount we'd have to take out of the atmosphere.
God, yeah, that's amazing. And we could actually go past 1.6 degrees, in which case we'd have to remove even more. Doesn't really seem likely, does it?
No, not at all. In fact, on the current path, we're probably going to end up needing to remove thousands of gigatons. Now, the third big point in this paper is that even if we did manage to do this and we removed enough CO2 to get temperatures back down again, that's going to take decades. So we're still going to have to adapt to and deal with those higher temperatures while they last.
And even adapting to what we've seen so far, relatively small changes, has been harder than we imagined it might be. Here's one of the scientists of the study, Karl Schlussner of the International Institute for Applied Systems Analysis in Austria.
And we also have an overconfidence in our ability to adapt to overshoot in the way we are currently framing and perceiving it. Because for adaptation, timescales matter. And any potential temperature reversal after an overshoot will take decades.
Now, Michael, we were on point 3. What's point 4?
The fourth big point is that bringing temperatures back down will not reverse all the changes that have happened. So the big one, of course, is that if more people die in extreme weather events or from starvation due to crop failures, there's no bringing them back.
Yeah, so we've got a quote from one of the scientists, another one of the scientists on the paper, Yuri Rogel of Imperial College London. Here's what he said about that.
Excess deaths are not reversible. So if you have a couple of decades which large proportions of vulnerable people are exposed to extreme heat in a society that is unadapted to this is not reversible. We show that based on the IPCC's own assessment of how the climate system can respond to our emissions, we know that for the same emission levels, there would be about a 1 in 10 chance that warming exceeds 2 degrees. So Simply by taking into account this information, a limited overshoot suddenly becomes much larger. A 1 in 10 chance of a potential existential threat is not small.
So, yeah, excess deaths are not reversible, and none of this is very good, is it, Michael?
No, and there are a whole lot of other changes that probably can't be reversed. For instance, if species go extinct, they're not going to come back, for all the talk of de-extinction. If ecosystems are damaged, they may not be recovered, at least on any human sort of timescale. And of course, higher temperatures will lead to even higher sea level rises in the following decades and centuries. The worst case scenario here is that by overshooting, we trigger one of the big tipping points, such as the collapse of the West Antarctic ice sheet or the drying up of the Amazon rainforest, which would just be impossible to reverse.
Yeah. Coincidentally to all this, I've just been reading a book called Overshoot. Overshoot, How the World Surrendered to Climate Breakdown. It's by Andreas Malm of Lund University, who he's been on the podcast, actually. He wrote How to Blow Up a Pipeline, and he's written that with Wim Carton, who's Professor of Sustainability, also at Lund. And I asked Wim how we got to where we are, and here's what he said.
This raises the interesting question of why we came to rely on these overshoot scenarios in the first place. Why did they become so dominant in this literature? And this is something that we explore in our own book, right? And we talk about the role of the economic assumptions that are built into these integrated assessment models, things like discount rates, etc., and how they essentially, normalize this idea that we should push emission cuts as far into the future as possible, and then overshoot became one way of doing that. And obviously, when small island states pushed for 1.5 degrees in the Paris Agreement, I hardly think they had an overshoot scenario in mind, right? They probably had a hard limit in mind. And the risk, of course, is that we see this logic being repeated for whatever limit comes next, right? 1.7 or 2 degrees. So, this normalization of overshoot, this hegemonic position of it in the models, has been really damaging, I think.
And I think another of the issues here is the way that modelling studies are used. So it's absolutely right that researchers use models to look at what it would take to get the planet back to 1.5 degrees. That's exactly what the models are for. That's the whole point of them, is to explore these kind of hypothetical scenarios. The problem is that the results of these studies are then presented as, here's a pathway to 1.5 degrees, even if that scenario in the model involves completely unrealistic assumptions. And then we end up with these policymakers and politicians telling us, here's the pathway we're going to follow, this is what we're going to do. And I think a lot of them actually believe that it's possible. For instance, it was clear even before the Paris Agreement was signed that limiting warming to 1.5 degrees was going to be very unlikely because it required really big and fast emission cuts. And there's now no doubt we're going to zoom way past 1.5 degrees. But we still got a few people saying, oh, well, it's achievable because, look, here's a model scenario in which it happens. Never mind that scenario involves these crazily big and fast emission reductions. And then as we zoom past 1.5 in the next decade or so, I think we're going to be told more and more now that we can still cool the planet back down to 1.5 with all these overshoot scenarios. But these claims, as we've seen, are just based on these sort of fictional scenarios where we can just suddenly remove these massive amounts of CO2. We just don't have the technology and we might never have it.
Well, I mean, if this overshoot paper cuts through, maybe we won't hear this anymore. People will understand when we actually can't get back down after overshoot. But if we can't, and we're seeing that adapting to higher temperatures is so hard, where does that leave us?
Yeah, well, it's bad already, and it's going to get a lot worse. But I'd say the crucial thing to end on is that there are a billion different shades of bad. So bad doesn't mean the world's going to end. Humanity's going to survive, and everything we do still matters. Every little bit of CO2 we keep out of the atmosphere means the future will be a little bit less bad. And so the take-home message here is that we need to redouble our efforts not to give up.
We've got an incredible story now about life forms discovered in 2 billion-year-old rocks. Sam Wong is here to tell us about it. Sam, where are these rocks, first of all?
The rocks are from northeastern South Africa in a place called the Bushveld Igneous Complex, which was formed when magma cooled below the surface of the Earth 2 billion years ago. These rocks have experienced very little deformation or metamorphic alteration over the past 2 billion years, so it could have been a pretty stable habitat. And some researchers led by Yohei Suzuki at the University of Tokyo drilled a core 15 meters below the surface and found living bacteria inside the core.
Okay, so it's the rocks that are 2 billion years old, right? We're not saying the microbes are that old.
Well, the team think that the microbes were carried into the rock by water shortly after the rock formed. And over time, the rock was clogged up with clay, which might have provided the necessary nutrients for the bacteria to live on. We know that microbes in the Earth's crust are extremely slow growing. Sometimes they take thousands or even millions of years to complete cell division. So no, they're not 2 billion year old microbes, but they are very old. We don't know exactly how old.
But couldn't they look at the DNA in the bacteria and find out?
That's what they're hoping to do. The team already know that the microbes are very primitive in evolutionary terms, but yes, they want to extract and analyze the DNA to learn more about them.
So this has got to be good news for astrobiologists thinking about life on other planets, right?
Yeah, so the rocks in the Bushveld Igneous Complex are very similar to Martian rocks, especially in terms of age. So it's possible that microbes are persisting beneath the surface of Mars as well. The researchers say that we should apply the same techniques that they've used to Martian rock samples.
There is a lot of life underground, isn't there, Sam? And I don't mean just in soil underground, but in rocks, in deep underground. And I remember this story that our colleague Graham Lawton did a few years ago, where they looked at data from hundreds of studies compiled from around the world. It came up with an estimate of the size of what they call the deep biosphere. Are you ready? The volume of that deep biosphere is twice that of all the oceans combined. So it's 2 billion cubic kilometers.
Incredible.
Yeah, and they estimated it's got 10 to the 30 microbial cells, and that's 70% of all microbial life on Earth, and that's in rocks.
Amazing.
Yeah, beneath the surface. So the subsurface biosphere, it's easily the largest biosphere on the planet.
Yeah, it's staggering. And these things, they have no source of energy except rock. So they live on timescales that are completely different to the ones that we're used to. And we know that some of them are living 4 kilometers deep at least, surviving extremely high temperature and pressure. But we've only sampled a tiny fraction of what's out there. So we really have no idea where the deep biosphere ends. There might even be entirely new domains of life waiting to be discovered down there.
Now, in other news, how likely are you to live to 100? Carissa Wong has been reporting on this. Carissa, what did you find out? Should I be planning for my and my twin brother's 100th birthday party?
Well, the long story short is probably not. In a study I covered this week, researchers looked at mortality data spanning from the 1990s to 2019, and they found that gains in life expectancy are actually slowing down in the 10 wealthier regions they looked at, including the US and Australia. This means that life expectancy is unlikely to ever exceed about 84 for men or 90 for women, and just a minority of people born nowadays will make it to the big 100.
Well, why is that?
Well, researchers don't all agree on exactly why. 2 researchers I spoke to said it's probably because in the 20th century we saw huge advances in medicine, such as the discovery of antibiotics and antiseptics, and much cleaner living conditions. So life expectancy rose pretty rapidly by an average of 3 years per decade, a period that researchers call radical life extension. But since 2000, further advances in medicine haven't had such a big impact on how long we live, and this is causing the slowdown, supposedly. This is paired with the fact that some researchers think we're approaching a fundamental biological limit to human aging.
But it sounds like not everyone agrees.
No. So one researcher I spoke to said the slowdown in the past decade may be more to do with governments enforcing cuts in social benefits and healthcare services, rather than us approaching the limit of human life expectancy. With the right policies that tackle poverty and improve social care, he thought the slowdown might not have happened. And another researcher told me he thinks there's no limit to how long humans can live. He just thinks we haven't invested enough in the right anti-aging research.
No doubt we should invest in his special method of life extension. So you mentioned they're looking at these 10 wealthier regions. What about within those regions? Were there any differences worth picking out?
Yeah, there were some differences. So the US saw the biggest slowdown in life expectancy growth over the past few decades, and that's potentially due to the ongoing opioid crisis, among other factors, according to the researchers I spoke to. But the picture's somewhat rosier in Hong Kong, which was the only place in the study that has seen a rise in the rate of life expectancy gain since 2010.
Why is that?
We don't really know, but one researcher involved in the study speculated it may be partly to do with people, for example, having better access to healthcare compared to elsewhere.
Okay, so I'm not sure if this is good or bad news. To be clear, we are still seeing increases in life expectancy. But what about increases in our health span?
Yeah, so we are still seeing increases in our life expectancy. So even if we're not going to all live to 100, we should probably celebrate the fact we can live this long. And in terms of health span, we are still having lots of therapies and treatments being developed that can boost our health. So I think on the bright side, there are plenty of ways to stay healthy while we are alive.
Let's talk about Hurricane Milton. It ended up missing Tampa, but made landfall on Florida's west coast as a Category 3 hurricane. It then passed over Florida and has left the East Coast, but it has caused immense damage.
Yeah, James Deneen has reported on this for us, is here now. James, what can we say at this point about Milton, about its intensification and how it drew all this power from the hot oceans, about how that's been boosted by climate change? Because I kind of feel I've not been seeing that link being made very much.
Well, there hasn't yet been a formal attribution study laying out what role climate change played in Milton's strength, but there's good reason to think it played a major role. One of the clearest is the extremely rapid speed at which Milton intensified from a tropical depression to a full-blown Category 5 hurricane just 48 hours later. This was a few days before it made landfall. And that intensification happened over an area of the Gulf of Mexico with temperatures far above average. This research organization, Climate Central, calculated that climate change made those sea surface temperatures 400 to 800 times more likely.
Wow. And Milton comes, of course, just a week after Hurricane Helene. And according to estimates by AccuWeather, it caused economic loss as high as $250 billion, as well as 227 dead over 6 states. Though, of course, those numbers are being tallied still today.
Right. Yeah, that's right. Some communities in Florida still recovering from Helene were hit by Milton in a compound disaster. And, one storm after the other like this feels all the more surprising given this surge of activity follows a bit of a lull in the hurricane season. Despite forecasts of a really extreme season, there was little hurricane activity between more or less late August and late September. There's been a lot of speculation about why that was. One possibility is a large amount of dusty wind from the Sahara Desert drying out the air. A delayed transition to the La Nina conditions in the Pacific Ocean may also have meant there was more wind shear tearing apart those storms as they developed than expected. But whatever the cause, that lull is clearly over. With Helene and now Milton, we've seen 5 hurricanes in just over the past 2 weeks. And just to add on to the one point on the climate question, there has been a formal attribution study for Hurricane Helene that found basically every aspect of that storm was made more intense by climate change.
Well, James, that leads me on to my next point. So last year, the Republican governor of Florida, Ron DeSantis, he famously struck out climate change from state laws. And at the same time, he watered down action on climate change. So what that makes me wonder is, with this very in-your-face experience of climate change across Florida, whether these hurricanes is it going to help Kamala Harris win Florida?
That's a big question. I think in some ways it would be too soon to speculate on that. I mean, the Milton is still affecting Florida. There's still tornadoes behind the storm. So, damages are still being assessed. But it has been really striking how this surge of hurricane activity has interacted with politics so near to a presidential election where what to do about climate change is already a key issue. There's been a lot of misinformation swirling around the federal government's emergency response to Hurricane Helene, for instance, with claims that relief funds are being withheld or have run out. And it's fair to expect we'll see more of that with Milton. The damages from both hurricanes could also affect whether people are able to cast their ballots in just a few weeks. And much will depend on how the disaster response plays out and really who gets the credit or who gets the blame.
Before we go, I wanted to flag up one thing that popped up since last week's show. We were talking about an experiment looking at coral adaptation to warmer waters, and we had a comment from coral biologist Terry Hughes. He said that the experiment we were reporting on was done in winter. Now, the biologist in Hawaii who carried out that work, Chris Jury, he got in touch with me after to point out that that was a mistake and that the warming experiments were in fact done in summer. So Chris asked us to correct that. We're happy to make that point and to reiterate that his work shows that some of the most common corals show the capacity to adapt to warming of about 1.1 to 1.5 degrees Celsius in 50 years.
That's it for this week. Thanks to all our guests and thanks to you for listening. Do tell your friends about us and give us a 5-star rating and a review on Spotify and Apple Podcasts.
And there's always more from New Scientist on our website, newscientist.com. We'll be back next week. Bye for now.
Bye.
This podcast is produced by OG Podcasts. Find out more at ogpodcasts.co.uk.